So last time we talked about postulate number 4, and postulate number 4 we said states that quantum mechanical operators that represent system properties have a complete orthonormal eigenbasis. Eigenbasis is just a set of eigenfunctions. Okay. Now, the only thing I'm really assuming here is the word complete. Okay, and that means psi can be expressed as a linear combination of the functions in your set of eigenfunctions, in your basis set. We've actually started to prove that because we are assuming the operators are Hermitian, we can actually prove that the eigenfunctions are orthogonal to each other. That was the last thing we did last time, right? And we can actually, of course, we can always choose them to be normalized. Okay, so last time we said that we can prove that the eigenfunctions are orthogonal to each other if they are non-degenerate. Okay, so this was the proof that we did last time. So if you have two eigenfunctions of a Hermitian operator, if they happen to be non-degenerate, if they don't have the same eigenvalue, then we can prove that they are orthogonal. Now, if they are degenerate, okay, they need not be orthogonal, but we can select a set of wave functions, a set of eigenfunctions that are orthogonal to each other. And every other possibility, any other eigenfunction that has the same eigenvalue can be expressed as a linear combination of these orthogonal eigenfunctions. Okay, so this is where we left off last time. So we said that if f and g are degenerate, okay, and linearly independent eigenfunctions, we're going to elaborate about linearly independent later, then a linear combination of f and g is also an eigenfunction. You already know that, right? So let's suppose that we have two degenerate eigenfunctions, but the integral of f star g d tau is not equal to 0. What if, okay, we're going to say what if f star g d tau is not equal to 0. That's possible if they are degenerate. Okay? If they're non-degenerate, we know that that integral is going to be 0. We've already proven it. But if they are degenerate, okay, see, if you go back to our previous proof, we've only proven it for non-degenerate case. All right, so what happens then? All we have to do then is we're going to replace g, instead of using g, so our functions would include f and g and so on, right? But we don't want f and g together because they're not orthogonal. So what we want to do is we're going to replace g with something else. We're going to replace it by k. Okay? And we're going to say that k is equal to the original function f plus some constant times g. We just have to know what that constant c is. So determining what that c is, okay, will give us this new function k, which we're going to use instead of g in our set of functions. Okay, so this procedure is known as the Schmidt orthogonalization procedure. So we're going to choose k so that, in other words, we're going to choose the c here so that f and k are orthogonal. So how can we make f and k orthogonal? What should be the value of c if f and k are orthogonal? Let's do it this way. We're going to say f and k is what? F plus cg, right? Must be equal to 0. So how can I simplify this? This is just a linear operator, right? So I can distribute. So I can write this as f star f d tau plus f star cg d tau integral equal to 0. Okay. And what would this be? Let's just solve for c. What can I do with c? It's a constant, right? I can pull it out of my integral. And finally, what do I do? Solve for c. It's negative of f star f d tau know, over the integral of x star g. Okay? Since we want, if we assume our functions are all normalized, then this is just going to be -1 over integral of f star. Okay, so that's our C. So that means instead of, okay, our functions, remember, instead of a set of functions that include f and g, okay, we're going to replace g by what? By k. So we're going to, instead of g, we're going to use f minus 1 over integral of f star g times g. So that is your Schmidt orthogonalization procedure. Okay? Now, remember we said that any linear combination of degenerate eigenfunctions is also an eigenfunction. Okay? So when we're specifying the set of eigenfunctions, we only specify the minimum possible number for a particular degenerate value of eigenvalue. Okay? So we only specify what are known as linearly independent eigenfunctions. What do we mean by linearly independent eigenfunctions? We started talking about that last time. Let me elaborate now what we mean by linearly independent. Okay? If I say that f is a constant times, let's say f1 is a constant times f2, okay? Then we say f1 and f2 are not linearly independent. So if it's possible to write f1 as a constant times f2, then they're not linearly independent. You only need one of those two functions in your expression, in your set. Okay? Now, what about if, let's say, if we say something like f1 equals c a f1 plus a f2 plus b f3, where a and b are constants. Okay? Then that means you only have two independent functions, f2 and f1, we say, is not independent of f2 and f1. Okay? Anytime you can write a function as a linear combination of other functions, then that function, we say, is not independent of the other functions. And so what we want to do when we specify an eigenbasis or a set of eigenfunctions is we should just list the minimum possible number of independent eigenfunctions for each particular eigenvalue. Because everything else can be written as, everything else for that particular eigenvalue can be written as a linear combination of those degenerate eigenfunctions that we chose. Okay? So let's look at this question, which will allow us to put together everything we've learned so far the last couple of days. Suppose you have an eigenbasis, f sub I, so this means the set f1, f2, and so on, okay? And let's say it's the eigenbasis for operator b, so that's b hat, okay? Such that, in order of increasing eigenvalues, let's say b hat f1 gives you f1, b hat f2 gives you 3f2, b hat f3 gives you 3f3, b hat f4 gives you 3f4, and let's say b hat, this should be f5, gives you 7f5, and so on. Okay, so that's in order. What's the eigenvalue for this one? This one, what's the eigenvalue? 1. What's the eigenvalue for this one? 3. And what's the eigenvalue for this one? Okay. So we say, what is the degeneracy of the second level? There are 3 eigenfunctions, linearly independent eigenfunctions, that have an eigenvalue of 3. Okay? And there's only one that has an eigenvalue of 1, right? So we say this is non-degenerate. We say this is triply degenerate. There are 3 linearly independent functions that have the same eigenvalue. What about this one? This is non-degenerate. Sometimes, here's the case where 1 is equal to 0, just because of the way we use words in English. When we say non-degenerate, we can also say that this is singly degenerate, because the degeneracy is equal to 1. Okay? So when we say the degeneracy is equal to 1, that means singly degenerate. We can also say it's non-degenerate. All right. So these are your eigenfunctions and eigenvalues. Okay. So what if psi happens to be? What if psi is equal to some normalization constant n times f1 plus 2f2 plus 3f2? Okay. According to postulate number 4, what is the probability of obtaining a value of 3 if I were to measure B? So the answer would be equal to what? Probability that I'm going to get B equals 3. Which of these eigenfunctions have an eigenvalue of 3? This one, f2, right? So it's going to be c2 squared. But f3 also has an eigenvalue of 3, so you can add to that the probability that you're going to get the eigenfunction, eigenvalue of f3, so c3 squared, right, plus c4 squared, because these are the 3 eigenfunctions that have an eigenvalue of 3. So, what would be the answer? What is c2 squared here? Okay, so C1 is equal to 1, is equal to n, right? What is C2? 2n. What is C3? 3n. What is C4? 0. Okay? So the probability that a measurement of property B will give us a value of 3 is going to be equal to C2 squared, which is 2n squared, plus c3 squared, which is 3n squared, plus c4 squared, which is 0 squared. And so what would that be? That's 4 plus 9 times absolute value of n squared, right? What is absolute value of n squared? Do you remember?
What is the last one, 0 squared?
C4 is 0. This is C1 F1, so C1 is n, right? C2 F2, so C2 is 2n. Remember, there's an n right there. And let me rewrite that. So we're saying psi is equal to n F1 plus 2n F2 plus 3n F3. I'm just distributing my n, okay? Right here. So that is C1 F1 plus C2 F2 plus C3 F3 plus 0 times F4, right? So C4 is, okay? So the fact that this is a 2 and that's a 3, that's just coincidence. Poor choice of, I guess, poor choice of numbers for me, got you a little confused there. So. But that's just, it's just the coefficient of function 2. So it is, in this case, it happens to be 2n, and then this is the coefficient of function 4 is 0. Okay. So what would be our, well, what do we do to determine absolute value of n squared? We normalize the function, right? Psi must be normalized. So what do you remember from the normalization? Integral of psi star psi d tau is equal to what? If your functions are an orthonormal set, this f1, f2, and 3 are part of an orthonormal set, what is this integral equal to? It's equal to 1, and that's equal to what? C1 squared plus C2 squared, right? Plus C3 squared, plus and so on. You add up all the C squareds, that should add up to 1. See, this is the probability you get the eigenvalue of c of function 1. This is the probability that you get the eigenvalue of function 2, plus the probability that you get the eigenvalue of function 3, and so on. Add up all of those probabilities, they should be equal. So, what do we get now? What is C1 squared? N squared, right? What is C2 squared? So that means 4n squared. We've already seen that, right? And what is C3 squared? 9n squared. And everything else would be 0, right? So that means that 1 is equal to 1 plus 4 plus 9, that is 14 times absolute value of n squared. Absolute value of n squared is 1 over 14. So to answer our, so what is n? 1. Absolute value of n is 1 over square root of 14. So to answer our question, we say the answer is, oh, that is n squared. So 114. So it's going to be 4 plus 9, 13 times 1 over 14. So 13 out of 14. So the probability that you're going to get 3 if you measure property B is C2 squared plus C3 squared plus C4 squared, because F2, F3, and F4 have an eigenvalue of 3. Okay? And so if you add up all those probabilities, you get 13 out of 14. Okay? Question? Where did this one come from? That's postulate number 4. Based on postulate number, it's postulate number 4. The probability of obtaining eigenvalue a sub I when a is measured is c sub I squared. So the probability that you get a2 would be c2 squared. The probability that you get a3 would be c3 squared. Okay? Well, in this case, let's see. The probability that you get an eigenvalue of 3 would be the probability that you get the eigenvalue of f2, which is c2 squared, plus the let's say that's 3. The eigenvalue of f3 is also 3, so you add the probability. Let me give you another simple example. Let's say, what if, okay, let me give you another example. What if psi is equal to normalization constant times 3f1 plus 4f3? Okay? What is the probability that the measurement of B will give you 1? That's just going to be equal to what? C1 squared. Okay? So what is C1? 3. 3n, right? So it's going to be 3 absolute value of n squared. So that's 9 absolute value of n squared. Okay? What's the probability that you're going to get equals 2. There is an eigenfunction that has an eigenvalue of 2. An eigenvalue of 2 is not allowed, right? So 0. What's the probability that you're going to get b equals 3? B equals 3, there are 3 eigenfunctions that have an eigenvalue of 3. So the answer there is C2 squared plus C3 squared plus C4 squared. The coefficient of F2 squared plus the coefficient of F3 squared plus the coefficient of F4 squared. Because F2, F3, and F4 will all give you an eigenvalue of 3. So what will be this answer right here? It's going to be 3n squared. Oh, sorry. What's the coefficient of F2? 0. Plus coefficient of F3? 4n squared. What's the coefficient of F4? 0. Okay, how do we determine n squared? So C1 squared plus C3 squared, is equal to 1, right? Because those are the only ones that contribute to your psi. So you're going to say then that what? C1 is how much? So you have 3 times 3n absolute value squared plus absolute value of 4n squared is equal to 1. Okay? So that's C1 squared plus C3 squared must be equal to 1. So that's 9 plus 16 absolute value of n squared equals 1. So absolute value of n squared is 1 over 25. So absolute value of n is just 1 over 5. So the normalized function here is what? What's another way of writing this normalized psi? It can be 3 over 5 f1 plus 4 over 5 f3. Okay? But that's not really necessarily the truth because we only know the absolute value of n. So this is just n. So it could have been, it could be a negative 5 instead of a 5. Okay? Eigenvalue. The value. Remember, our postulate says if you measure B, the only possible outcomes are the eigenvalues of operator B. Okay? Alright, so let's talk about expectation values now. The expectation value, or the average value, is also known as the average value of the property of the system. Okay, can be obtained by imagining you have a large number of identical systems. That means they all have the same psi. Okay. Imagine you have a large number of identical systems, they all have the same psi. Measure that property for each one of those systems. Okay. How do you get the average? The average of property A. So each one of those systems, although they all have the same psi, will not give you the same A if you measure A, right? Because of the probabilistic nature of these things. So the average value of property A would just be the sum of each possible outcome. What are the possible outcomes? The eigenvalues of A. So you add up each possible outcome multiplied by the probability of that outcome. So the probability of obtaining base of I. That's really how you take an average. Right? So let me just see if we can relate that to something more familiar to you. Let's say calculating an average. Let's say possible outcomes are, okay, let's say this is representative of the outcomes. Okay, let's say you measured several times. Okay, so you got 2, 2, 3, 3, 3, Okay, and let's say if you keep doing it, you keep getting a 2 or a 3, and let's say this is a representative sample. So what's the probability that I'm going to get a 2? 1, 2 out of 5 possible outcomes, 2 out of 5, right? Okay, what's the probability that I'm going to get a 3? 3 over 5, right? So what's my average? If I were to do this lots and lots of times and always get a 2 to 3 ratio, so your average A would be what? What would be the straightforward way of doing it? You say 2 plus 2 plus 3 plus 3 plus 3 divided by 5, right? But what's another way of doing this? I can say this is 2 happening twice, right? Plus 3 happening how many times? 3 times. Divided by the total number of times everything happened is 5, right? Well, I can write it this way. 2 times 2 over 5 plus 3 times 3 over 5. Okay? This is one possible outcome. This is the probability of that outcome. So this is the probability of getting a 2, right? This is possible outcome. It's a 3. 3 is one of the possibility, right? So possible outcome multiplied by the probability that I'm going to get a 3. So you add up each possible outcome multiplied by the probability of that outcome. That's how you get the average, right? So, question? What's not equal? Which one? The first line and the second line? This is 2 times 2, and that's 3 times 3, and the denominator is 5. Huh? Okay. Okay, I guess those 2s and 3s are confusing. Let's do 1 and 5. Okay, 1, 1, 5, 5, and 5. So what's the average here? You can say 1 times 2 over 5 plus 5 times 3 over 5. So if this is representative of a very large number of measurements, then you say 2 out of 5 will be the probability of getting a 2, getting a 1, right? So this is 1. So your possible outcome is a 1. And this would be the probability of getting a 1. Right? Provided that this particular set is representative of the whole large number of measurements. Okay? So that is your expectation value. That's how you calculate the average. Okay? So, but what do we know about the probability of A sub I? That's the summation of A sub I times C sub I squared, right? Where big psi is just C1, F1 plus C2, F2, and so on. Where F1, F2, and so on would be the eigenfunctions of whatever operator, of operator A in this case. Okay? So let's take a look at this one. We can actually prove that psi star A hat psi, or this, you can write in bracket notation like this, It's just the expectation value. Okay. Now, in most books, this is actually the expression of the postulate, and then from that you can derive postulate number 4. Okay, because this would suggest postulate number 4 that you can actually show that that's C sub I squared. Okay. But in our case, we made the assumption that C sub I squareds are the probabilities. Then we can prove this instead. It doesn't really matter. You can take one as a postulate and prove the other, or you can take the other one as a postulate and prove this. I think your textbook does use this as a postulate. Okay? So, and then the Born postulate is also a consequence of postulate number 4. We'll get to that in a minute. Let's look at this one right here. Okay? So let's show that that is in fact the case. Integral of psi star psi star a hat psi d tau. Okay, let's put this in bracket notation. Integral of psi star a hat, and what's my psi? C1 F1 plus C2 F2 plus and so on and so forth, right? We're going to say that a hat F1 is equal to A1 F1, where A1 is one of the eigenvalues, right? And so on. So, which one? Yeah, I have a star.
It's not supposed to be shown.
Oh, that's right. You're not supposed to show the star. Okay. Sorry. Yeah, you're right. No star because it's already inside the bracket. Correct. All right. So now, what would this be? C1 a hat F1 plus C2 a hat F2 and so on, right? And what do we do next? Operate on all of them. So C1 eigenfunction is, let's call it A1, little A1, F1, and A2 hat operate A hat F2 would give you eigenvalue A2, little A2 times F2 plus and so on and so forth. Okay? And what do we have on this side? This is going to be what? C1 F1 plus C2 F2 plus and so on. I have C1 A1 F1 plus C2 A2 F2 and so on and so forth. Okay? So what can we do? We can split this up, right, into little parts. So if you put this one and this one together, what do you get? C1 F1, C1 A1 F1. What would that be? Okay, I can pull out my A1, right? And C1 squared. Remember, this C1 has a star, and that C1 has no star. So C1 star times C1 is absolute value of C1 squared. And I can pull that out of my integral. And what do I have left? F1 star F1 d tau, which is just going to be 1. It's the function. Okay, why can you pull out the A? Because it's standard notation. This is going to be integral of C1 star F1 star C1 A1 F1 d tau. Okay, so this C1, A1, and C1 star, those are all constants. You can pull them out of your integral. Okay? So what about this second term right here? So that's the first term. How about this one? You can see there you're going to have a what? That's going to end up 0. Why? Because you're going to have a C1 star, C2, right? And then A2, and then you're going to have F1, F2 left inside the bracket. So that's going to be 0. So all the cross terms are going to come out 0, right? So what will happen here then? You'll just have, and this is just 1, so this is just A1 C1 squared plus A2 absolute value of C2 squared and so on. So that's just the sum of A sub I times the probability that you're going to get A sub I. Okay, since absolute value of C sub I squared is the probability that you're going to get A sub I. And since that's the expression you get, that is the average. So that is your expectation value. So to get the average or expectation value of property A, all you have to do is this. Apply operator A on whatever psi is, multiply by the complex conjugate of psi, integrate over all space. Okay? Now, the Born postulate, we talked about the Born postulate earlier, a few lectures back. What did we say the Born postulate was? Psi, that's psi squared, absolute value of psi squared is a probability density function, right? More specifically, we say that it's, remember we said that absolute value of psi squared dx is the probability of finding that particle between x and x plus dx, right? So let's see why that is a consequence of this postulate. That's why we did not give a number to the Born postulate, because we can just derive it from here. Okay, so we can say then that let's calculate the average location, average x value. How do we get that? Integral of what? Psi star x hat psi d tau, right? So it should be automatic, okay? If you want to calculate the average of anything, put it between psi star and psi, integrate over all space. So what would this be? Well, it's just a multiplicative operator. So this is just psi star times x times psi d tau, right? And what would that be? That's just integral of x times psi squared d tau. And d tau is really dx from negative infinity to infinity. Okay, so I'm just going to call this dx then, from negative infinity to infinity. Well, does that make sense? This is, remember, definite integration is just addition over a continuous variable, right? So this is the sum of all the possible x values from negative infinity to infinity times the probability of getting each one of those possible x values. Okay, so the probability of getting a number between x and x plus dx is psi squared dx. Okay, so that explains the Born. That's how you get the Born postulate out of what we would call postulate 4. So this must be a probability. So you interpret this as probability of getting a value, a location between x and x plus x. Okay? So if you have a continuous variable, you integrate. If you have discrete variables, you sum. This one? How did I get that? That's a multiplicative operator. When you apply x hat on function f, it's just x times f. Remember, coordinates are multiplicative operators. Location. the operator for, that's postulate number 2, number 3. Go back. And again, yeah. So, yeah. Cool. The corresponding quantum mechanical operator for a coordinate is just a multiplicative operator. Okay? All right. So that's how you get expectation value. So let's apply those ideas now to this question. Let's say A hat f sub j gives you back j times j plus 1 alpha times f sub j. So f sub j, since j, allowed values of j are 0, 1, 2, 3, and so on. So we say that, what are the eigenvalues? So A f0 is equal to what? What is 0 times 0 plus 1 times alpha? 0. What is A hat operating on f1? So that's going to be 1 times 1 plus 1 times alpha. So that's 2 alpha. 2 alpha f1. What is A hat operating on f2? It's going to be 2 times 3, so that's 6 alpha f2. What is A hat operating on f3? 3 times 4, so that's 12 alpha f4. So those are your possible outcomes, right? 0, 2 alpha, 6 alpha, 12 alpha, and so on. So let's say psi happens to be 1 over square root of 6 f1 plus 2f2 plus f3. Okay, so what is our C1 here? 1 over square root of 6. What is our C2? 2 over square root of 6. What is our C3? 1 over square root of 6. Now, is psi normalized? What is C1 squared? Let's just verify that psi is normalized. What is C1 squared plus C2 squared plus C3 squared? 1, 6 plus 2, 6 plus 4, 6 plus 1, 6. So that's 6 out of 6. So psi is normalized. Okay? What's the expectation value of A? It's going to be integral of psi star A hat psi detail, right? Which is going to be sum of possible outcomes, A sub I times the probability of getting A sub I, which is C sub I squared. So what would that be? So it's going to be A1 times A1 times 1 over square root of 6 squared, right? Plus A2 times 2 over square root of 6 squared plus A3 times 1 over square root of 6 squared. So what is A1? A1 is 2 alpha, so that's your A1, this is your A0, this is your A2, 6 alpha, and A3 is 12 alpha. So it's going to be, note that we're ignoring A0 and A4 and A5 and others because the probabilities of those would be 0. The coefficients are 0. So this is going to be, what's A1? 2 alpha times 1, 6. What is A2? 6 alpha times 4, 6. What is A3? 12 alpha times 1 over 6. So that's the average value of A. Okay, so if you imagine you have a whole bunch of these systems, an infinite number of these systems, all having the same psi. Make measurements from each one of those systems. and you make a tally of all the outcomes. And this will be the average you'll get, which is going to be how much? You can do that on your own. All right. What if psi is equal to F2? Same situation as before. What if psi happens to be equal to F2? What's the expectation value for property A? Psi star A hat psi equals F2 A hat F2, which is F2 A hat F2. What is A hat F2? F2, little A2 F2. Factor out A2, F2, F2, and that's just 1, so it's just A2. So we say property A is well defined. So it has a definite value. If psi happens to be an eigenfunction of A, what we're saying here is what? If I were to do A hat psi, I'm going to get A2 times psi, right? Because psi is F2. So if psi is an eigenfunction of the operator, it has a well-defined value. What is that well-defined value? Whatever the eigenvalue is that corresponds to that particular eigenfunction. I'm sorry. So it's just going to be A2. And so in this case, what was A2? J plus 1 alpha. It's going to be 6 alpha. Okay? So if psi happens to be an eigenfunction of an operator, then if you measure the property corresponding to that operator, you'll get exactly what the eigenvalue is. That's the only possible outcome you'll get. So we say the property has a definite value. Okay, do we have time? Plenty of time? Okay. So now let's talk about commutators and how these are related to the concept of uncertainties in measurements. The commutator of two operators, A hat and B hat, okay, is represented by this symbol right here. So you separate A and B by a comma, put them in square brackets. So that's called the commutator of operators A and B. That's another operator, and the outcome of that operator is the difference in applying A first and then B compared to the situation where you apply B first and then A. Okay? So if I were to say A hat, B hat operating on function f, then you're going to say, okay, I'm going to do B first on function f and then apply operator A. And I'm going to switch the order. I'm going to do A first, apply it on function f, and then do operator B on the result. So that's what commutator means. So the commutator is just another operator. It's the sum of these two products. It's the difference of these two product operators. So what's the commutator of x and px? You should be able to show that that is equal to IH bar. And let's see if we can do that. Commutator of x and px. Okay. So let's apply that on a function of x. What are we supposed to do? We do xpx first and then subtract px x, right? So apply that on f, apply that on f. Right? So what do we get? What's the px operator? So this is x hat times x hat operating on and px operating on f. What does that do? H bar over I d by dx, right? Derivative with respect to x. of function f, okay, minus, what does this do? It's just a multiplicative operator, right? So px hat, so I just multiply f by x. Okay. Next step, what does the multiplicative operator do? Just multiply. So this is just going to be equal to x times h bar over I times derivative of f with respect to x. Let me put f. Let me keep putting f in blue here. H bar over I d by dx of function f. Okay. Minus, what does the momentum operator do? Takes the derivative with respect to x and then multiply the result by h bar over I, right? So I'm going to take the derivative of x times f. What's the derivative of a product? First times the second plus the second times, first times the derivative of the second plus the second times the derivative of the first. So let me rewrite this. So this is h bar over I, I'm going to say x times df dx, right? Minus h bar over I, and this is going to be x times derivative of f with respect to x. So that's first times the derivative of the second plus the second, which is f, right? Times the derivative of the first, which is dx dx. Okay, and so let's do some simplification. That's 1. Okay, and what do we have now? So this is equal to h bar over I x times df dx minus h bar over I, so I'm going to distribute this, right, times x df dx plus negative h bar over I times f. Well, what do we see here? This and this are the same, but there's a minus sign. So what do we have left? Which is equal to negative h bar over I times f. So that is the result, we say, of applying the commutator of x hat and px hat on function f. Right? All it does, this particular commutator, all it does is it multiplies the function f by negative h bar over I. Okay? So we say, but what is negative h bar over I? What's another way of writing that? It's just I h bar, right? Right? So times f. So all this commutator does is it multiplies the function by I h bar. So you could say that this commutator is a multiplicative operator. Multiplies it by I h bar. It's right there. Okay? H bar, remember, is h over 2 pi. I can't type h bar on the computer, so that's why I have to keep writing h over 2 pi. All right. So that's a commutator. So that's how you derive a commutator. You just apply it, and then when you get to the end, you have an operator. You end up with an operator on a function. So whatever that operator is, that's the definition of your commutator. All right. So what's the significance of commutators? If operators A and B happen to commute, okay, then we say that the commutator of AB is just a null operator. It just multiplies the operator by 0. Because if A, B, F, if A, B, F, and B, A, F are the same, regardless of what the function is, okay, this F right here must be an arbitrary function. It cannot be any specific function. It doesn't have, shouldn't be just one specific function. It should apply to any function, okay? If this happens to be 0, we say that the commutator is a null operator. Then we say that those two operators commute. Well, if that is the case, you can prove that it's possible to precisely determine A and B simultaneously. Okay? And the reason for that is we can prove that if two operators commute, then you can find a common complete set of eigenfunctions for them. So you can find a set of eigenfunctions that would be eigenfunctions of A, and there also happen to be eigenfunctions of B. Okay, if that's the case, remember, if psi is an eigenfunction of A, then measuring A will give you a definite value. If psi also happens to be an eigenfunction of B, then measuring B will give you a definite value. So if you can find a common complete set of eigenfunctions of A and B, then it's possible to measure A and B simultaneously very precisely. Right? Get an exact value for A and B. So that's the significance of commutators. So since X and Px do not commute, right? Then we say it's not possible to simultaneously determine X and Px precisely, which is our uncertainty principle. Okay? So that leads us to our postulate 5. Is it time to go? Okay, so postulate 5, we're going to cover that next time. We're going to talk about the uncertainty principle expressed in terms of commutators.